Today I am going to discuss about a resistance triggering circuit. In case of resistance triggering circuit, we can vary firing angle alpha from 0 to 90 degree. We cannot increase the firing angle alpha beyond 90 degree in case of resistance triggering circuit. This is the circuit diagram of resistance triggering circuit. Here, the anode and cathode of AC are connected to the supply through the load. This is the main circuit, and gate is connected to the control circuit. Here you can see here the resistance R1 is the fixed resistance which is used to control the gate current whenever R2 becomes 0, and R2 is the variable resistance. By varying this resistance, we can vary the firing angle alpha, so we can vary the output voltage which appear across the load. And here diode is used to protect the gate cathode junction during negative half cycle. And R is the stabilizing resistance which is used to control the gate voltage of ACR. So here R1 should be such that the gate current should not exceed its maximum possible gate current. So current will flow whenever R2 becomes 0. The maximum gate current will flow, that is Vm by R1 whenever R2 becomes 0. It should not exceed the maximum possible gate current, that is Ig max. This amount of current SCR can be withstand. So here Ig max is the maximum possible gate current. So R1 is less than equal to Vm by Ig max. Here Vm is the peak value of supply voltage and Ig max is the maximum possible gate current. And R2 value and resistance R should be such that the gate voltage should not exceed the maximum possible gate voltage of ACR. So maximum voltage appear across the load is equals to, that is Vm peak value divided by R1 plus R into R. It should not exceed the maximum possible gate voltage, that is Vg max, where Vg max is the maximum possible gate voltage. The gate of ACR can withstand this maximum voltage Vg max. So Vm R is less than equal to Vg max R1 plus Vg max R. So R is less than equal to Vg max divided by Vg max R1 divided by Vm minus Vg max. Now operation and waveform. Here, this is the supply AC sinusoidal waveform. Vs is equal to Vm sin omega t. And initially, ACR will be off state condition. So current will flow through the control circuit, and whenever voltage across R is reaches the gate triggering voltage of ACR, so ACR will be turned on and current will flow through the power circuit, and we'll get the output voltage V0 across the load. So suppose the gate triggering voltage of ACR, suppose this is the gate triggering voltage VGT. Whenever voltage across R reaches this gate triggering voltage, so ACR will be turned on. So whenever R2 is very high, so peak value appear across R, that is equal to Vm by R1 plus R2 plus R into R. That is the gate peak voltage VGP. VGP, gate peak voltage. Actually, the voltage across R fed to the SCR gate to turn on the device. So if supply voltage is sinusoidal, so obviously voltage across are also sinusoidal, and Vg, the voltage across R, is equals to, we can write VGP sin omega t. So here VGP, gate peak voltage, is Vm into R by R1 plus R2, R1 plus R2 plus R. So if R2 becomes large, so peak voltage is less, which appear across R. So it does not reaches the gate triggering voltage, that is VGP is less than VGT, gate triggering voltage. Next, during negative half cycle, the voltage appears does not appears the voltage across the gate, because diode is connected here. We'll get only during positive half cycle, and again we get during positive half cycle, but does not reaches the gate triggering voltage. So load voltage becomes 0 whenever R2 is large. Load voltage becomes 0, and voltage waveform across the thyristor, that is the supply voltage appears across the thyristor. The same waveform appear that is the waveform across the thyristor. And if we decrease the resistance R2, so VGP, gate peak voltage, that is the peak voltage across R, will be increased, and whenever reaches the gate triggering voltage of ACR, so ACR will be turned on. This is the gate triggering voltage VGT. So whenever VGP, gate peak voltage, appear just reaches this voltage, so ACR will be turned on at an angle alpha. Then again we'll get here So SCR will be turned on at an angle alpha. So we get the output voltage. Just follow this input waveform from this angle, like this. Next we get here. So voltage appears across the thyristor during up period. We'll get the voltage, and whenever turn on becomes 0, then again we'll get negative voltage. Then again we'll get during up period, again becomes 0, like this. And if we decrease the resistance further, R2 value decrease further, so the peak value across the R, VGP, is greater than the VGT, gate triggering voltage. Gate triggering voltage. This is the gate triggering voltage. ACR will be turned on at this voltage. So if R2 is decreased further, so VGP now in this condition, the VGP is equals to VGT, gate triggering voltage, and here VGP, gate peak voltage, is greater than the VGP is greater than VGT. So gate triggering voltage reaches at this angle. So ACR will be turned on here. Next again we'll get turn on here. Next ACR will be turned on here. So you get the output voltage. Just follow from this angle of input waveform, like this. Next again we'll get here. Here alpha is less than 90 degree. In previous case, here alpha is equals to 90 degree. And what will be the waveform across the thyristor during up period? Voltage appears across the SCR, then during on period, voltage becomes 0, then appear during negative half cycle, then during off period, we'll get the voltage, then again 0, and again appears negative half cycle, like this. So we can vary the firing angle alpha from 0 to maximum 90 degree in case of resistance triggering.